The problem that we're going to discuss today is chef and queries. The problem appeared in June 21 starters and has a difficulty level of easy medium. The prerequisites to solve this problem are Fenwick tree or popularly known as binary index trees. The problem statement goes as follows. We are given an array A consisting of n elements, and now chef wants us to handle Q queries of the following types. So the first query is an update query. Let me just quickly write here. This is an update query, and here we have to report the ith element. So here we have to report. So this update query, it's basically a range update, because you can see that in this type of query, first of all, the query type is 1 and it will be followed by 3 integers, that is L, R and X. So what we have to do is, for all I in the range L, R, including the endpoints as well, we have to add x plus I minus L whole square to A of I. So to each AL plus 1 all the way up to AR, we have to add x plus I minus L square to the AIth element. So whenever we get this query, we have to make this range update, and whenever we get the query of type 2, we have to just output the ith element. So the query of type 2 is accompanied with just one integer, that is I, which tells us that we have to report the ith integer, that is print AI. So that is pretty much the question. And in the we have to note that for the first type of queries, you don't have to print anything. Just make the changes. That is, just make the updates in your array. Don't report the answer. Now this is the question. It seems pretty small, but also have a look at the constraints. So the size of the array and number of queries both can range up to 10 to the power 5. So brute force method is not going to work. That is, you cannot just iterate, that is run a for loop from L to R and make all the updates each time. You need something else. So definitely we need a better data structure to handle these range update queries, and we have to point query, right? Range update, and we have to query a particular point, that is ith index. So this is pretty much the question. So the solution approach goes as follows. First of all, we need to ask this question to ourselves, that how to do range update and point query efficiently. What do we mean by range update? Range update means that whatever array I am having, I am making the updates to this array in a particular range. That is, let's say from some range L to some range R, to these many elements. And whenever I am reporting my answer, I am doing a point query. That is some particular ith element. Correct. So this is called as range update and point query. So how do we do this efficiently? There are many data structures that you can use to do the same, but the one that is most easy to implement and well known is Fenwick trees. So this is one of the data structures which is quite famous for these kind of operations, that is range update and point queries on arrays. So this is a prerequisite for this question, but right now we don't know how to use Fenwick trees in this question. So we are just going to keep it as a tool to ourselves. Whether to use it or not, let's see. Now let's have a look at the update query once again. So the update query was that we have to add x plus I minus L whole square to the aith term, where I belongs from L to R. That is, we have to make these updates to all the elements from AL to AR, right? All these elements. So let's just focus on the particular ith element. So for ith element, this value is going to be added. So if we rearrange the terms, we can write this as I plus x minus L whole square. So if you open this, this will turn out to be I square plus x minus L whole square plus 2 into I into x minus L. So we have got three different terms in our square, correct? So now maybe some of you might be getting hint that how Fenwick tree can be used. But if you are not getting any hint, no problem. We'll see that how Fenwick tree plays a role in solving this problem. So imagine that if the problem was very simple, that you will be given the query that is L and R, and what you have to do is just add X to all these elements. That is, add X to AL to AR. In that case, this is basically standard Fenwick tree, right? That is, you are given the indices and you have to add just one particular value to all of them. But here, there are three different values that we need to add to these ranges, AL to AR. First of all, we need to add I square from each I belonging to L to R. Then we need to add X minus L square to each of these elements, and also we need to add these to all of them, and in them I is a variable, correct? This is invariant because it does not depend on the index I. X minus L whole square for a particular query of type 1 is fixed, correct? So the only part that is varying is I, because if I is 1 then it will be 1 square, if I is 2 it is 2 square, but this term does not depend on the value of I. Similarly, in the third term as well, this part that is X minus L, this one is independent of I. So the way we are going to implement these range updates is that directly we are not going to add X plus I minus L whole square uh, in our Fenwick tree. Rather, we are going to break it in three terms. One is I square, one is this X minus L whole square, and the third one is this. Now, in their individual contribution to the addition to AI can be maintained by using a total of three Fenwick trees. So one Fenwick tree will be to calculate what is this contribution, second one for this, and third one for this. Let's see how. So assuming that our Fenwick tree has the following two functions, that is, first of all, range sum. That is, we'll give three parameters L, R, and value. So what this range sum function will do is, it will add the value val to all the elements from index L to index R. So this is our function, assuming that it is in our Fenwick tree implemented, and there is one more function known as get. So what this function will do is, it will tell me currently what is the value of my ith element after doing all the updates that we have done before. Okay, currently what is the value? So assuming that there are these two functions, now we can see that how using three Fenwick trees we can maintain the collective changes that these three terms are bringing to our elements. So first of all, for the ith element, always this term I square is added. So let's say if my value of I was 2, that is the second element, and my L comma R in one case is, let's say, 1 comma 5, then in this range as well 2 is present. If my L comma R is 2 comma 7, in this range also 2 is present. In each case, always I square is only added. It is independent of X and L. So always 2 square is added for I is equals to 2. So we just need to maintain that how many times a particular index has been a part of a range. So whenever we get a range L comma R, for all the indices from L to R, we'll just increment their count, that is increment by 1. Okay, so in that case, what will be our query for the Fenwick tree? This will be maintained in the first Fenwick tree. So the query will look like the Fenwick tree 1. So let's say ft1 dot range sum, and we have to do the range sum from L to R, and we have to just maintain a count that how many times each element from L to R has been counted. So we just increment these values by 1. So this is my first Fenwick tree, and this will be responsible for calculating the change brought by this I square term. Now for the second term, that is x minus L square, just simply we have to do the query like ft2 Fenwick tree 2. Let's say our second Fenwick tree. In that we have to do the range sum from L to R, and just this constant value, because it is not going to change, x minus L whole square. Just add this value to all these elements from L to R in my second Fenwick tree. So this will handle this effect. Okay. Now for the third one, I is variable. So I cannot just add 2 into x minus L into I to each of them, because for each of them I varies, right? And my range sum function, as you can see over here, the range sum function, it just takes the 3 parameters. So we have to be smart. Now, how to do that? In the third Fenwick tree, what we'll store is the collective sum up till now for all the queries, that is L comma R, and 2 into x minus L. So once we have these 3 Fenwick trees with us, after doing as many as update operations that you want, that is, we have 2 type of operations, right? If you remember, the question has 2 type of operations. One is 1 LRX and the second one is 2Y. So each time you get an operation of type 1, you have to perform these 3 operations, that is, make the 3 updates in our Fenwick trees. So the collective effort is then stored, and whenever you get the operation of type 2, that is, you have to report the ith element. Now you have to combine all these efforts, all these terms. How to combine them? Now the answer will be, first of all, the initial element was ai. Then how many times have you added the I square term? The I square term, we have added a total of ft1 dot get I. These many times I have added I square to my ith term. So that is my first term effort. The second term is x minus L square. So just simply write ft2 dot get I. And for the third term, we have to combine I with ft3. So how do we write that? You have to write it like, I can write over here I, which is my current index, into ft3 dot get I. So this is the final expression that you will get. Let me just highlight it. So once you have these 3 Fenwick trees with you, all you need to do while reporting an answer is get the original element ai from Fenwick tree 1, get the count, how many times I square was added, what is the total value of summation x minus L square that has been made till now. Okay, how many times, all the sums will be present in this second Fenwick tree, and in the third one 2 into x minus L sum will be present. So just multiply it with I to get the actual value, that is 2 into I into x minus L, all these sums till now. Okay, and that's it. That completes our solution. So now let's see how to implement the same in C++. So the implementation that I have here already uses a template for Fenwick tree. So this is my standard implementation for Fenwick tree, which contains the function which initializes my code. Then I have this function known as range add, which basically takes 3 parameters L, R, and val, and adds the element val from L to R, all elements. And also I have the get function to get the current ith element, okay, which I provide, the index which I provide. So this is the template for Fenwick tree. Just a point to be noted that all the queries to this Fenwick tree should be 0 based, although the internal working is 1 based indexing. So all the queries, that is L comma R, should be 0 based. Now let's get to the main code. Main code is basically a reflection of what we saw in the solution. All the syntaxes are same, everything is same. First of all, take the input for n and q. Then create our three Fenwick trees which are initially empty, all the elements are 0. Then take the array input of size n, and then for each query, first take the query type. If the query type is 1, then we have to take three inputs again, L, R and X. For these three numbers, I consider Y as X minus L. Then I decrement L and R because I want my index to be zero based, and then I do the three update operations in my Fenwick trees. So L comma R comma 1 in the first, L comma R comma Y square, that is basically X minus L whole square in my second Fenwick tree, and in the third one 2 into X minus L, so 2 into Y. And these three operations are done whenever I get type 1 query. Whenever I get a type 2 query, I just do A of I minus 1, because again, even though the input that I'm getting I is 1 based, the elements are actually stored in 0 based indexing. So AI, that is basically AI minus 1, plus I square into Fenwick tree 1 value, then Fenwick plus Fenwick tree 2 value, and then plus I into FT3 value. So the queries made are in 0 based, so you can see I minus 1, I minus 1 and I minus 1 everywhere. And that's it. Whatever we have discussed in this solution, just a clear reflection of the same. Just that you need some template for Fenwick tree. You can write your own code or take it from the internet as well. But just make sure that your queries are perfect. That is, you don't have to make silly mistakes that like 0 based indexing and 1 based indexing. So you have to be careful there. And that's it. This completes our solution. Now, let me tell you about CP tutorials that we have at CodeChef. So if you're new to programming, you can head over to this page over here and you can find many topics like backtracking, binary search, and even Fenwick and segment trees, the topic required for today's question. So if you don't know this topic, you can head over to here and learn this from our expert educator. And if you want even more structured content, you can always opt for our plus subscription on Unacademy, where you can use my referral code Darshan 25 to get instant 10% discount.